Intensive Prolog is a multimedia package of interactive video, a course text, a workbook, a set textbook, computer software, and a reference manual. The video cassette is divided into 4 30-minute interactive sessions. At the start of the first session, we consider this simple Prolog program. And the query is Bedford en route to Rome. Frank Kravacek and Malcolm Dixon take up the story.
So here's our initial goal. And here's what the Prolog interpreter does. It introduces a procedure status box. Notice the 2 clause branches at the bottom of the procedure box, showing there are 2 en route clauses. The clause counter is set at 0, showing neither has been tried yet. The computer must now search its database, looking for a match for this goal.
What I'm going to do here is handle the database search. The method used by Prolog to search its database is as follows. Set the clause counter to 1. Go to the database and take a copy of the first en route clause and bring it over. Now compare it with the goal. Does it match? Well, that's a job for the unification program.
No, it doesn't match. Rome doesn't match Bedford. So dead end the first clause branch and discard the clause.
So now increment the clause counter again. Go over to the database and take a copy of the second en route clause and bring it over. Now this en route clause contains variables p, a and np, and to avoid possible confusions in taking this copy, I'll subscript all the variables with 1. P1, P1, A1, NP1 and MP1. Now, does this match?
Yes, this matches because P1 is a variable and can be instantiated to Bedford. So, put a clause status box on the second branch. You can subsequently tick it or cross it, depending on the ultimate outcome of the processing of this clause branch. The goal en route P1 can only succeed if the 2 sub-goals in the body succeed. So, the program now starts building itself a tree reflecting this goal-sub-goal relationship. P1 is instantiated to Bedford, and this must be done in both places P1 appears. The sub-goals are now processed one at a time. It starts with move Bedford A1 and P1, which becomes the new focus of attention.
So it's another database search. Set the clause counter to 1. Take a copy of the first move clause, bring it over, and compare it.
No, this doesn't match. Bedford doesn't match home, so you'll have to dead end the first clause branch and discard the clause.
Increment the counter again. Take a copy of the second move clause.
Yes, this is a match. A1 can be instantiated to train and NP1 to Gatwick. So put a clause status box on the second clause branch. So a match has been found for move Bedford A1 NP1 with some instantiations. A1 is instantiated to train, and NP1 is instantiated to Gatwick. Notice that NP1 occurs twice, so NP1 must be instantiated to Gatwick in both places. The left-hand goal now succeeds because move Bedford train Gatwick is a fact. There are no further sub-goals to be derived on this side of the tree. So we can tick the clause status box and also the procedure status box. But there's a second sub-goal to test on the right-hand side of the tree. So we now shift our attention to this other sub-goal.
And so on until eventually the query en route Bedford succeeds. In the second video session, we look at how the route finding program used earlier can be expanded to include a how, so that a list of actions used on a route can be output. Marc Eisenstadt explains the execution of the query.
What we're going to do is to try and illustrate the way in which the variable how becomes instantiated in successively greater detail during each recursive invocation of routes. We've built this bank of TV monitors to display the workings of a Prolog program. To begin with, we'll pick up from where Malcolm began. This was his query, and we've seen a match with clause 2 of routes. Remembering that all variables are subscripted, we've instantiated place 1 and finish 1. In order to accommodate the ever-lengthening lists, we've had to continue the line on a second screen, but the intention is to read right across. Let's look at the first of the two sub-goals. The first one is move from one place by an action to a new place. One of these variables was an input variable, so as it's already instantiated in the head, place 1 would have immediately been instantiated as Bedford. Clause 2 of move is the first match since the move starts at Bedford, and that match instantiates Act 1 to train and new place 1 to Gatwick. Now, in fact, all occurrences of Act 1 are instantiated. This means that within the third argument of the top goal, Act 1, which is in the head of the list, is instantiated to train. And we'll see that more Acts 1 becomes successively more instantiated at each recursive invocation. So now Prolog will have to check the second sub-goal to start to find the tail of the list. That's more Acts 1. And this is just what's going to happen. This time, our search for matching clauses finds a match in clause 1. And this is where more Acts 2 is instantiated to the empty list. Everywhere it occurs. So now we know what more Acts 1 is, namely the list whose head is plain and whose tail is the empty list. And this is true everywhere that more Acts 1 occurs. How is then instantiated to a list whose head is train and whose tail is the list we've just seen. And that is Prolog's output in answer to the query. In fact, this is beautified to simply train plain. So that's demonstrated successive instantiation in some detail, although to the outside world, the appearance is, of course, just one of two inputs and one output, with the list of actions train, plain being output.
Video 3 is concerned with harnessing backtracking. An example using member is used as one illustration.
This is where we can harness backtracking to our advantage. To generate our solutions, what I do is make this query part of a larger conjunctive query. So I have the query member x a, b, c, d, e. Then I have the instruction write x, and now I tell it to fail using the primitive fail. So, running this program, x is instantiated to a via x1. Then a is displayed on the screen, and then a failure occurs. So the program is forced to backtrack, looking for alternative ways of making this conjunction succeed. Write is one of those primitives which cannot be redone on backtracking. So, member must be retried. So, this clause branch will be failed, and now a match will be looked for using the second member clause. But to see this in action, we really need to look at the sequence of AORTA diagrams from start to finish. This composite query splits into a tree with 3 linked branches. Looking at the first goal, member x, a, b, c, d, e, this matches on the first member clause with x instantiated to a. Now the program writes out this value for x. And now the program encounters the fail primitive. For the top status box to succeed, all 3 below must succeed. But fail can never succeed, so the program now starts backtracking. Write cannot be redone, so it fails, and we backtrack further. In fact, we backtrack to this clause status box, where we last had a successful match. This clause fails, and we reset the procedure goal to a query. So, carrying on, the interpreter increments the clause counter and brings over the second member clause. This causes the tree to build up. Now, X's 2 is instantiated to the list B, C, D, E. The interpreter now processes the lower procedure box. It brings over the first member clause. It matches, with X2 and X3 instantiated to B. So ticks work their way up the tree. Now the program writes out B, and then fails. So backtrack. Back the program goes to the last successful match.
What you have seen are just small sections of the video in the multimedia course on intensive Prolog. The whole pack includes 2 hours of interactive video, a course text, a workbook, a set textbook, computer software, and a reference manual.